I arrived at Harvard as a graduate student in 1971 and had the lucky or unlucky draft number of 32. So nobody here probably remembers what that means, but it means that I was being offered an all expenses paid tour to Southeast Asia. So when I arrived, I thought I'd be here only for a year. And I got lucky, that's a long story. But when I came here, I thought I would be doing mathematical physics. But I took John Tate's course on number theory, starting out with local fields, and I was hooked. So after I got lucky and was really here, I started working with John. So at that time, the Langlands program was, of course, coming into kind of full force. That was very popular. And, well, some of you know this history, and now I'll try to make this device work for me. So I'm not going to be terribly technical about things. For instance, new forms that have to really do some work to make this completely precise, but I'm assuming almost everybody here has had some exposure to him. There were a couple of cases of the Langlands program that seemed approachable. Of course, elliptic curves and modular forms of weight 2, but also the modular forms, odd modular forms of weight 1, and two-dimensional odd Galois representations. Deline and Serre came out with a preprint that showed that if you had a modular form of weight 1, then you could get a Galois representation. And well, how could you get a modular form of weight 1 of the right kind? Nobody really knew. However, there's a special case of a far more general theory. It was known that if you had a Galois representation of the right kind, and it and all of its twists satisfied Artin's conjecture, namely their L series were holomorphic, then you could find a modular form of weight 1. But Artin's conjecture wasn't really known for any truly non-trivial Artin representations, so this seemed kind of an interesting point of research, but first of all, I should talk about what the Galois representations look like. Since it's continuous, one of the many things I didn't mention, that means it factors through a finite group, and finite Galois group of L over Q, and you can project that to the corresponding subgroup of PGL2, and if we're talking irreducible representations, that means it was either dihedral or one of the groups of symmetries of the Platonic solids. And well, what was known about Artin's conjecture for those? Well, dihedral is induced, so for sort of formal reasons, there was no problem with those. The other three were complete mysteries. And here is a picture of the corresponding fields, so I get to name K and L with that picture. So at John's urging, several people, namely Jerry, Jim, Dan, and Robert, I believe, took the smallest possible conductors for tetrahedral and octahedral representations, and there was a very busy team with, Tate coming and enjoying all of the excitement and some of it in the Commons room, and they verified those examples. So that gives you some confidence that it's a sensible way to look at the world. And later, starting a year or two later, Langlands showed, using not the modular forms language, which is certainly easier for a graduate student to understand, but the automorphic forms, representations form of this, that because the A4 is solvable, really, you can base change. And that fairly easily can be used to, easily is an overstatement, but can be used to show that all tetrahedral extensions are, fit the one-to-one correspondence predicted by Langlands. Later, Langlands and Tunnel did the octahedral case, again using the automorphic language, and that required a little more work in that case. It wasn't quite as simple as pushing up or restricting, however you want to think of it, to the extension. You had to play with more groups to make that all work. So this actually was not complete for several years, but it sort of showed how you would handle the tetrahedral and octahedral cases, and pretty much didn't require you to have the base field to be the rational numbers. So what about the icosahedral case? Now, for reasons I'll explain in a moment, I wasn't in that active in that group because I was starting to use the computers that had been installed downstairs. And at one point, I went into John's office and I said, well, would an icosahedral example be interesting? And well, of course, for the same reason the earlier examples were interesting, just kind of as a sanity check, but John got really excited. And I was actually slightly taken aback by that, but I didn't yet know that he really liked his Hewlett-Packard stack-based calculator and become very adept at doing lots of interesting things. I mean, he could pull it out and show you some cute little, number theory, but he could pull it out and show you some very non-trivial number theory. Joe gave a very good example. So he was really happy about this idea. And so what do you have to do? Well, in that tower of fields, the first thing you have to do is find, in this case, a quintic polynomial whose Galois group is the alternating group A5. But then you have to lift it. Now, in the tetrahedral and octahedral cases, that's not too hard to see what you should do. In the case of A5, well, first of all, the degree is very large. You're not going to be looking at polynomials of degree 60 in some variable or something. And there's a little, well, I would now call it an exercise, but determining the minimal conductor of a lift, first of all, reduces to local questions. And most of the local questions are trivial, but exactly one isn't. They had published a paper in Inventiones Exercices Diadiques, where he had looked at the finite extensions of Q2. And the only ones that were interesting from this point of view were A4, well, and not S4. There are 3 S4 extensions of Q2 and 1 A4, and S4 doesn't fit inside of A5, so it's not going to be the decomposition group of some prime. So really there's one interesting case from the point of view of all the lifting work I had done. And it had to be over 2, and it had to be a polynomial that had the right reduction of 2 so that applied. So once you've figured out what the minimal lifting is, what are you going to do? Now you really know the L series, so you know what the Q expansion is of your putative modular form of weight 1. And how are you going to find it? Well, the same trick that had been used in the earlier case in doing examples, namely take a bunch of easy to understand modular forms of weight 1, multiply them by your supposed 1, you get a form of weight 2, and if you do it right, it'll really be something you can recognize. And then just say your form of weight 1 is the quotient. But of course then, how do you know that's holomorphic everywhere? And so there are a couple exercises. You have to think about the cusps and show there are no common zeros of the divisors, and that doesn't turn out to be very hard. So that's the plan. But just now stepping aside, I'm going to say, first Unix installation outside of Bell Labs was across the hall here. Technically, the one in the chemistry department might have been earlier, but the group here was a very eclectic group of very bright computer-oriented people. I was not really one of those, but I knew most of them, I mean all of them in short order, because this was an opportunity to have a very powerful computer in relative terms. I mean, my goodness, 32K it did have to contain both your program and memory. And of course, there's no math software on it. So you're not going to be able to do anything that you would now do with Sage or any other system solve linear equations, even have polynomials. You're going to have to construct absolutely everything by hand. But the atmosphere there was quite different from the bigger computers down the road, where if you wanted to run your pack of punch cards, you had to know somebody and get in their grant or put it at the end of the list. And then, of course, if you were just learning things, you would fail the first time. And the amount of time to do that cycle was absolutely prohibitive. Whereas this more free floating operating system allowed you to fail numerous times very quickly. And the programming language C was very down to earth. Now, people who did Algol and Pascal, to teach programming kind of would look down their nose at that because it was not quite as pure and robust and able to catch errors as C. But if you wanted to really grab onto the hardware as best you could, C was better with that. C would know there was an underlying machine and let you access that, whereas Pascal would rather you didn't know there was an underlying machine, is how I would put it. And I learned how to program C about, I would say, starting 9 months before anything appeared about C. And the way I would do that would be to show up early in the morning, because almost everybody except me were real, stay up all night kind of people. In fact, one of them had their main job was being a rock musician. And so they would have their gigs and come here at midnight or later and start programming. And I would, try my thing, and of course it wouldn't compile or it would fail to run. And then I would ask one of them, and then I'd try again, then I'd ask another one. That's a very good way to learn. And so before the Kernahan and Ritchie book came out, I was a reasonably competent programmer. And I just enjoyed that environment. So I think this really enabled the computations of the first icosahedral modular form. People would sometimes come down and watch. And John would come down and watch, but certainly the most nerve-wracking case for me was one time when Sayre, who was here a lot during that time, in fact, the whole year. And so he came down one Saturday afternoon, because I told him I'd be there, and he sat behind me and just watched. And that was kind of nerve-wracking, because, what happens when you program? Well, you type something in, it doesn't compile, you swear at the screen, a couple of rounds of that, then it compiles. And then it runs, and it gives you complete nonsense. You get negative feedback and you get better fast, but still. Anyway, Sayre seemed to enjoy it, so that was good. He just kind of wanted to find out what it was like. So the first step to find the icosahedral representation is finding a quintic. Now, I never really figured out a good way to do that. So somebody wants you to find a polynomial of Galois group A5. Let's just start off with that. What do? Well, you probably put intervals around each of the coefficients. You might even say to yourself, gee, for the first one, I can make it non-negative without loss of generality. There's simple things you can do. If you start thinking harder, you tend to allow the ones towards the constant end to be run through a bigger interval. And this problem vexed me and is part of the topic I'll end up with a little bit, only in the sense that my vexation about finding quintics led me to keep thinking about that after I'd finished. Okay, so in all the ones that I looked through by, ranges that nowadays would seem small, this one really stood out. And applying all, the lifting stuff, first of all, the decomposition group at 2 was A4. So at least that was nice. In fact, I would have used this even if I had known that there were smaller ones. I'll give you the data on, in fact, what the truth is about the icosahedral conductors. And of course, I really like the factorization 2 to the 5th times 5 squared, with my draft number hiding there. By the way, yesterday I checked, because it was my impression from long ago. By the way, I'm talking about things where, how do you remember things from that far back? But this seems to be the best model of it, despite the fact that it's not integrally closed either at 2 or at 5. The discriminant of the polynomial, in other words, is larger than the discriminant of the field. And at least Sage couldn't find a Chernowsen transformation that improved it. Okay, so that was the polynomial. I was going to use it no matter what. And, I'll come back later to how close that actually was. Now, I have to make a slight digression here. Probably most, but not all of you know that Yogi Berra was once upon a time a catcher and then a manager for the New York Yankees. That's baseball. He had a goofy, he would come up with goofy things, but he did that with sufficient frequency that became known as something that you could ascribe a quote to Yogi and everybody would believe he must have said that. Okay, you can get, I think, more than one book with his quotes. And only few of you may know is that computer scientists have discovered that he anticipates all of their discoveries. And you probably know this, yeah. And so I'll give you, just to the one I'm going to use, I have to get you warmed up for what their flavor is, both in what Yogi said and how the computer scientists have decided to label them. They will say he discovered quantum computation because supposedly he said, when you come to a fork in the road, take it. Okay, or here, this is clearly very apropos debugging. You can observe a lot by watching. So in fact, if you stop swearing and just look, you can debug your programs. Or much more current, he discovered nuclear neural networks much earlier. You don't know where you're going, you might end up somewhere else. Anyway, there's a whole book of these. But the one that is most relevant to me was ascribed by computer science to the problem of, what does big O of n and big O of 1 mean really? And actually, I think of this as applying to finding icosahedral Deligne-Serre examples, by which I mean finding the modular form and not just the representation. In theory, there's no difference between theory and practice. In practice, there is. So the theory is pretty clear. Namely, you construct, if you find a Quintic polynomial, take its Galois closure, you have an A5 extension of Q. The resulting extension you're looking for is cyclic. It turns out that to really calculate that, and you're going to have to know that to know the coefficients of the L series, it's very good to look at the sextic field inside the A5 extension. And of course, this brings you back to all this Horyol theory of the sextic resolvent of Quintic. And the whole exercise was just a lot of fun, a lot of beautiful algebraic number theory. And in fact, the key computations on the sign, what you really have to do to find the L series is to go down and compute in, well, a class group, a generalized class group in the sextic field. And that was the most interesting, that was a very interesting part of the calculations. You had to figure out all the algebraic number theory, especially you didn't readily have a good model that was integrally closed everywhere. And then you're in this free abelian group, and I'd certainly implemented things like polynomials and linear algebra, just in having to get this far. But doing free abelian groups modulo something, that was a very interesting exercise to implement that efficiently. Of course, nowadays, first of all, it's done for you, and it doesn't sound like that hard a problem, but really doing it was tough. So the plan, as I sort of already mentioned, is figure out what the minimum lift was, and that really pushes down to E, and then do the same thing that they did in the earlier cases, find several different modular forms, F1 of weight 1, multiply by your putative modular form, and then get a modular form of weight 2 in level 800. Now, it turns out the dimension at 800, gamma naught of 800 is 97. And now, so what you're going to, first of all, be looking for is to find that your modular, putative modular form matches what can be found in that vector space. And I did it out to, 360 places just to pick a big number. So first of all, the big goal is now going to be, boom, find that linear dependence. And okay, well, all these things were hard then with the tools at hand, but a lot of fun. And it turned out the lifting of minimal conductor wasn't the one of least degree, so all the computations had to be done over the eighth roots of unity. So no big deal, but still, it just turned out the right thing to do was use the Chinese remainder theorem for primes congruent to 1 mod 8, and a lot of them, and that worked. And the task of finding that linear dependence was so exciting when it hit. And John was paying very close attention to everything I was doing. At one point, when he realized the magnitude of the computations, he said, oh my God, this was really not a thesis topic. And by then, I was so confident it was going to happen. When he suggested another thesis topic real fast, I said, no, I think I'll stick with this. And the relief on his face was enormous. But he felt obligated to at least allow for that possibility. Now, what levels did I miss is an interesting question. And according to LMFDB, I missed, 5 of them. These are all icosahedral examples. And, why did I miss them? Well, there are 2 things that I really would have liked to save from all of this. And one is, what were the ranges I actually searched? I kept a fairly good record of that. And the other thing was, I somehow, as a side thing, I had looked at the problem of finding the ring of integers, because when the sextic field, you're quite z adjoint alpha is quite far from the ring of integers. I didn't really need anything other than the decomposition of the primes, but it was still a good exercise. Maybe at one point I thought I was going to need that. So I did a whole lot of work on making that reasonable, at least enough at the time, and I had that program in fairly nice shape, and so now, anybody tell me what's going to happen? Well, what storage media did I have it on? Drew's nodding his head. It doesn't matter. So I had it on a deck tape. So this big machine, it was a huge machine, as tall as me and like that. Had a little deck tape. It was like a magnetic recording tape. And of course, that machine was replaced in the course of doing all this, and then it was a different kind of faster mag tape. So all of my thesis work was on it, including a list of not only polynomials I've searched, but I decided to go up to conductor 10,000. And there were a lot of those. And I kept the ones that were even. In other words, that potentially could be on the other side of the modularity question, which nobody was thinking too hard about at that point. So I was surprised a few years, 20 years ago, when I saw this. How long ago was it? Maybe not quite 20, 15 years ago. I don't know why. I can't explain it. I would have thought I would have captured those, but I didn't. And of course, what happened to the mag tapes? Well, they said somebody over in psychology could still read them. So I went over there and talked to him. He said, no. In a way that didn't lead me to want to try. I mean, I couldn't push him to do it. It wasn't like I could pay him money. I think they'd been stored in too hot environment and they'd kind of slightly congealed. Anyway, all of that was lost. So I can't answer the question that I've been asked several times. Why didn't I discover that? Or discover these? But of course, I would have done 800 anyway because of the lifting application. There are lots of funny stories about the computations at that time and the Science Center. I got very used to coming in early in the morning so I could talk to the right people and then going about my day and coming back next morning and having people come down and talk to me and gradually getting some other people at least started doing algebraic number theory calculations of this kind. When I came up to John's office and said, the linear algebra has worked, he was ecstatic. There were still a lot of things to do, but that was a very exciting moment for both of us. Okay, I'm zipping through things, but I have other things to say, so I'll have a little more time. So all along, the question of how do you search quintics, how do you find their roots, had sort of burrowed into my mind. In particular, would there be any intelligent way to do this if you had a better understanding of that? Well, first of all, just the problem of solving quintics is interesting. You can find several different ways to solve quintics involving taking, well, 2 square roots and then solving a 1-parameter family of quintics. And what were those devices they had in the early 20th century where you could adjust a parameter and solve a cubic? Nobody's going to, it's too old-fashioned. It was, what's that? No, early 20th century. And you know, if for some surveying reason, whatever, you're going to always be solving a cubic, let's say a cubic equation. So you reduce it to a 1-parameter form, and then you have this dial that rotates and it gives you a root of the cubic. And there's a name for that. And people thought about some of Kronecker and Klein's ways of thinking about quintics and wanted to do the same thing. I'm not sure how practically motivated it was, but it's kind of, they wanted a universal 1-parameter family of quintics that was, they didn't regard taking square roots or cube roots as of any consequence. So you know, I should have looked it up. There's some strange term there for that. That motivated some of this. Reduce a quintic to a 1-parameter family. Well, Sayre has an elegant little article about these accessory irrationalities. But I bugged him about the following question, which popped up. Can you reduce the general quintic to this particular form? you've not only knocked out the x to the fourth coefficient, but also the x squared coefficient. Now, if you ask to knock out the first two coefficients, in other words, the coefficient of x to the fourth and x cubed, well, you're not going to be able to do that with a totally real polynomial because the sum of the squares isn't going to be 0. So that is not going to have the property. You're going to need to adjoin a square root, and in fact, an imaginary square root to do that. And everybody kind of knows about the Bring-Girard form, which reduces to x to the fifth plus ax plus b. Well, that requires some square roots along the way. Oh, and by the way, I would call that one parameter because by scaling, you can make them equal. Similarly, I would call this 2 parameters. By scaling. So, well, that was interesting. You know, on the back of my mind, I'm saying to myself, could I have made my searches on a very primitive computer go faster if I'd searched this way, if I'd only searched these? You'd expect that maybe the ones that you'd find would be a little higher, but you could search much further. And Serre thought that was a good question and sent it to Cray, who proved the answer was yes. It's a question about twisted forms of the cubic surface, sum of 5 variables, and the cubes of those 5 variables are 0. That's a cubic surface, and roughly this says twistings, the appropriate sense of twistings, this always has rational points. That's a little surprising. Any further reduction along these lines doesn't seem possible. And the natural generalization to 7th degree polynomials, kick out the terms of weight 1 and 3, does not seem to work. So it was a very nice idea, but it was at that time kind of, what does this mean? And the common room then was different than the common room now. And so, as we know, there are many generations of Tate students here, and it seems like you can identify 4 or 5 separate clumps that will all say that they were here in the golden age of Tate being an advisor. I think I was in the second one, maybe. The common room, when we moved into the building in my second year, had 3 offices off to the west. And Brouwer was in one of those offices. He was quite old. And I said, gee, that must have been kind of hard for him. He was moving slowly. And because, there was ping pong and yelling and screaming in the common room. And Tate said, no, he thought it was the perfect place. Same with Zariski, because he was sort of hard of hearing. So nothing would disturb him. But I was told at dinner last night, I think it was dinner, that Dick was in the far office there for a while. He would leave his office door open, didn't mind at all when the ping pong ball came rolling in there. In any event, Brouwer's last paper, which he finished in that room, was the following question. And maybe I want to go back here and say that the first 2 bullets are pushing towards the question of if you're going to allow yourself k-parameter polynomials for free. In other words, you can adjoin the root of an algebraic function that depends on k variables, but you can do it many times. What's the minimal k you can get? But the last one is a different question. Namely, the question there is, I'm only going to give you one algebraic shot, but you have to solve it with that one. You're not allowed to iterate. So the resolvent degree is the first one, and the essential dimension is the second one. So those are different ideas. And So Richard Brower was working on the resolvent degree, and his paper in 76, which he said was, surely just scratching the surface, was he could reduce a logarithmic number, the number of parameters n by something approximately log n. So in some sense, a trivial improvement. And there were specific conjectures by Hilbert on various examples. And so the resolvent degree over the complex numbers of 5 is 1, because 2 square roots in a single parameter family, you only had to allow 1 parameter. And Carré's form is 2 parameters, but only one, you get it in one shot. Can you do better than that? Well, the resolvent degree, it really seems like a tough question. And Mark and Benson and Drew and a number of other people have really hit that hard, and they've come to the same lower bound that everybody else has. Namely, it's at least 1. Yeah. And how big is it? It seems to be slowly increasing, and it's a big open question. And I should say, both with resolvent degree and essential dimension, you can find the idea occurring elsewhere. So, for instance, to ascribe this to the recent work, not quite right, because you can find that elsewhere, but they've really, thrown a lot of stuff and found a lot of interesting results about that. In the case of essential dimension, it's a different idea. And with resolvent degree, you can ask Mark, and he will tell you that lower bound 1 is going to be awfully hard to reach. And it just seems to be a situation where it is very hard to make improvements that approach what you might think would be true. Essential dimension is a different notion. It's a little more flexible. Merkuriev, first Zinovi found it applied to algebraic groups. Sayre got excited. Merkuriev found it was really functorial in a very interesting way. So it's more flexible. Even if it's not quite answering the question that you might want, it's led to a lot of work. I didn't think I was going to have a lot of time, so I guess I'm going to end more quickly than I thought, and you can have more time for lunch. But these two issues, there's a lot to say about them. And one recent advance, including Oakley Edens, who's here, somewhere here, a first-year graduate student here, and Zinovi recently have shown that the upper bounds, which nobody thought for essential dimension, can be improved in characteristic P. So the definition can be applied in a lot of contexts, and at least in that context, it can be improved. When Zinovi and I started working on it many years ago, right away we were surprised that by quite easy argument, roughly speaking, you could prove n over 2, ceiling of n over 2 as a lower bound for the essential dimension for the group S sub n. So there's these two notions that sort of come out of this, and progress on either of those would be absolutely fantastic. So thank you very much for your attention.